This Week in Radio Tech, episode 301, is brought to you by Lavo and the Crystal Clear Virtual Radio Console. Crystal Clear is the console with a multi-touch touchscreen interface. By Omnia Audio and the full line of Omnia audio processors for AM, FM, streaming, and studio. Hear the music and not the processor with Omnia. And by the Axia Fusion AOIP audio console, where intelligent function meets beautiful design. Now with AES67 built in. IP audio security is a hot topic. IP audio reliability is a strong concern as well. Keyur Parikh from GatesAir is working with a team of IP media experts to mitigate impairments to IP transport and tells us about technical defenses against IP audio hacking. Hey, welcome into This Week in Radio Tech. I'm Kirk Harnack, your host, and I'm delighted that you're here, and I'm glad I'm here. We've got a great show today. Chris Tobin is along, of course, as usual, our terrific co-host from an undisclosed location in the New York City area. And we've got a great guest coming up, too. We'll introduce our guest in just a moment. First, I want to tell you, this is episode number 301 of This Week in Radio Tech. It's the show where we talk about everything from the microphone to the light bulb at the top of the tower. You know, I guess I could have put the foam sponge on the mic. I took it off. There may be diseases on it, so I took the sponge off, the pop filter. As usual, Chris Tobin is with us, and we'll get to Chris in a second. I want to explain I'm in a different location than usual. I believe I've done 2 or 3 of the shows over time from this studio. This is the studio of WKXY in Cleveland, Mississippi. Cleveland, Mississippi. Small town, about a 2.5-hour drive south of Memphis, Tennessee. And Cleveland is famous for Delta State University. And now Cleveland has the Mississippi Grammy Museum here. It just opened up a few weeks ago. It's Cleveland. It's called the Jewel of the Delta, cute little town, and growing a little bit at a time. So a big agricultural area, too. That's where I am at WKXY in Cleveland, Mississippi. Been doing some engineering work down here and putting more stuff to use from the Telos Alliance as well. We'll talk about that later. All right, Chris Tobin, the best-dressed engineer in radio. Welcome in, dude. How are you?
I'm good. Thank you. Yes, I'm at a transmitter facility here in New York City. I'll have to keep it that way. That's about it. That's all I can say. But you can see the transmitter behind me. Right above my head here is the backup transmitter. So fear not, there's no RF from that one. It's the one on the other side of the room. And then there's a lot of IP things here and familiar. This is wacky processor some guy designed, and it's just, it's very loud. That's all I can say.
Okay. Are you in a place that, do you have antennas maybe some floors above you?
Absolutely. There's a huge spire just above me, about 3 floors up, and it protrudes above the skyline of Manhattan, and there's lots of stuff up there. There's Master FM, a UHF, VHF TV, single FM antenna, and a few backup stuff. And then there's the usual federal government agencies that are spotted all around the rooftop as well.
Sure. All right. Well, good deal. Chris, we got a great show. Just before we started with the official start of the show, I was prefacing you that about a year ago, I was at the NAB show during the Broadcast Engineering Conference, and I delivered a paper myself about a satellite and terrestrial WAN system, distribution system in Australia. And so I hung around and thought, hey, here's an interesting program coming up. A gentleman by the name of Keyur Parikh was going to be talking about modeling of network impairments, packet losses. And as someone who works for Telos, this was kind of interesting to me because we do some modeling at Telos as well. But I was really interested in this scientific paper from Keyur Parikh and also co-authored by Junius Kim, and from both of them from GatesAir. So time went by, and I finally got around to talking to Keyur Parikh and getting him on the show. So let's bring him on in. Welcome in, Keyur Parikh from GatesAir. How are you today?
I'm great. Thank you for having me. I'm glad to be here.
Well, I'm glad you're here, too. A few weeks ago, we talked with your colleague, Rich Redmond, and he did a great job. I've known Rich for years, but I've only recently met you, so glad that you're here.
Yeah, I'm glad to be here again. Yeah.
So give us a little preview, and I'm sorry, I forget the order we were going to talk about our 2 subjects. One was security for IP media, and we've had some, that's been in the news here lately for broadcast engineers, and also this thing about modeling network impairments and things you can do to to mitigate those impairments. Which one do you want to talk about first after our
So
first break?
we can start with talking about packet loss impairments modeling. I think that's probably the topic that we had discussed. We'll start with the first half, and then we'll move on to the network security side.
Perfect. Perfect. All righty. Good deal. Well, we'll talk about that in just a minute. Our show, This Week in Radio Tech, episode number 301, is brought to you in part by the folks at Lavo, L-A-W-O. They're a German company that makes audio consoles. They've introduced some new concepts in virtual radio at the NAB show, and I'm not at liberty to talk about those yet. So we're going to talk about the Crystal Clear console, which is actually their first foray into giving you a virtualized mixing surface. So the Crystal Clear audio console from Lavo is this console that has two parts. And that's becoming very popular nowadays. There's a surface that is what the talent touches and adjusts and moves, knobs, or in this case, a touch screen with the Crystal Clear. And then there's another box that goes in a rack somewhere, and that has your audio inputs and outputs. And in the case of the Lavo product, it's the Crystal mixing engine. So it's got the inputs and outputs. It has the DSP to do all the mixing. It's got all the logic and smarts that understand what to do with commands from the surface, which is either a hardware surface, or in the Crystal Clear case, it's a software surface. And the mixing engine, the Crystal part, also has power supplies. They have dual power supplies available. And there's a networking jack on there. Now, what can that do? Well, the network jack, of course, is where it talks to the rest of the network for monitoring and access and configuration purposes, but it also talks to the work surface. That is the clear part of the Crystal Clear. That's a good-sized touch screen. It's a multi-touch touch screen, so you can touch a number of faders at the same time. It'll actually handle up to 10 touches at once. I don't think mentally I could do 10 accurate touches at the same time, but it will handle that. Most people are going to be pushing up one or two faders at the same time and turning a monitor pot up or down, and the headphones, up or down. But you can also select on that surface, you can select what the characteristics of an input will be. You can change a mic gain, for example, or pan a mic a little bit left or right, as you might need, or change the way a backfeed is working to someone on a codec or someone on a telephone. So all these things are available right from that touchscreen surface. It looks like a console, like a very modern, beautiful console, but you just touch it. And because it's on the network, you can pick that touchscreen up and unplug it and move it to a different room if you like. So if you need to do your breakfast show from your office, you can actually do that. The other part, again, the rack mount part, the Crystal part, it has this network jack, talks to the surface, but it also talks AOIP. So you can bring in AES67 and, of course, send AES67. It also does Ravenna. And if you have Ravenna, you have almost everything with AES67 as well. So it does all that from the clear box, the Crystal box as well. If this sounds interesting to you, and to a lot of folks it does, go to the Lavo website, L-A-W-O, lavo.com, and click on products and look for, under radio products, the Crystal Clear console. On that page, there's that video in the top right corner of that page, and that's Mike Dosh, and he does a wonderful job of explaining how the Crystal Clear console works and what its benefits are. Thanks to Lavo for sponsoring This Week in Radio Tech. All right, Kirk Harnack, Chris Tobin, and our guest, Keyur Parikh, is with us from GatesAir. And so let's just jump right into it. Keyur, so this paper that you delivered last year, the role of network packet loss modeling in reliable transport of broadcast audio. Man, we're all interested in using IP, but we want it to work. We don't want, packets lost and audio to cut out. So could you brief us a little bit on, what your research was and what you found out?
Yeah, so this all started when we first introduced forward error correction schemes in our codecs, and as we were testing in the lab, we noticed that FEC schemes were not effective for certain patterns of losses when we used Gilbert-Elliott packet loss impairments with the Shunra network emulator. So we knew that the FEC schemes were not going to be effective for some type of patterns of losses. So we needed to have a method to calculate this model in real time on operational networks, so we would know on real real networks, whether the FEC schemes that we have will work on that network or not. So that was really the start of the research that we started research on that, and we came across a brilliant paper by 3 or 4 graduate engineering students from Rome, Italy, I believe. So they had a paper discussed various modeling techniques that are out there, including Gilbert-Elliott, and they introduced the 4-state Markov state model as a new alternative, new method that had a better representation of today's network versus the 2-state Gilbert-Elliott model, which has been around for since late 70s. So along with the paper, we were actually able to find algorithm in public domain, open source. So we were able to implement the algorithm that calculates the parameters of the model, so we can actually get our hands around the patterns of the losses, and in both in the codec as well as in our network analytics software. And there's a large support for that also in the Linux routers, with the NetM module. So we had a situation with cross-platform interoperability. We would use the Linux routers, to inject packet loss patterns in the lab, and we would actually measure the same parameters that we input in the routers in our codec. So it gave us, a confident feeling about our ability to measure the patterns of the model, which then allowed us to, collect this information from the real network, some customer's network, and bring that back into the lab and recreate the situation to improve the quality. Essentially, this was really the genesis of why we embarked on modeling the packet loss pattern, is to fully understand under what circumstances would the forward error correction work, and under which circumstances we have to use additional techniques that we have in our toolkit, such as interleaving that spreads out the losses, which would then make the FEC more effective, or our stream splicing technique, which is packet duplication scheme that sends duplicate packets not just across diverse network connections, but also across the same network with time diversity. So you can program in time delay between the duplicate packets, which is very powerful technique to absorb the burst losses if you know the time delay to apply, right? And that's where our network analytics, which we'll talk about, comes into picture.
I wonder if we might circle back just a bit and explain a few of you ran through a bunch of nice big words and concepts quickly. One of those was being that Markov model, the 4-state Markov model. And you had a great, I realize we can't show it right here on the show, but you had a great graphic that explained periods of burst and periods of gap, and then what happened in these different periods, and just typical modeling. And I guess I could say, okay, you've got an IP connection, and one of the possible impairments is you just lose a single packet every now and then, right?
So those are isolated losses. Those are isolated losses. Those are what we consider isolated losses. So at a high level, right, the Markov 4-state Markov state model has 4 states, but there are only 2 main states, just like Gilbert-Elliott. There's the burst state and there's a gap state, and then within the main states there are 2 substates. So this is where either you are getting a packet in that state, or you have lost a packet in that state. So the burst state is a state that you enter when you lose more than one packet in a sequence of packets, and your gap state is your quiet period, your normal state of the network. This is where you have uncorrelated isolated losses. So typically, if you have any type of forward error correction protection on a stream, gap state losses should be easily recovered. So the most important state is the burst state, and the 2 parameters that measure the intensity of the losses in the burst state are burst density, which is the probability of losing a packet while you are in that burst state, and in a burst size, which is a duration of the state in either time or the packet. So I think if I give an example, it would clear up a little bit more.
Yes, please do.
So let's so let's take an example. Let's say there is a model that has 1% average packet loss rate with 15% burst density, and let's say, for example, the burst size is 300 milliseconds or some number. If you compare this with 1% average packet loss rate with 80% burst density, same burst duration. You can ignore the gap state losses for now because they are not important. They can be easily recovered. Now, both 1% average packet loss rate. If you measure them over maybe a 24-hour period, and this is what typically your ISP will tell you, well, we have 1% loss or 0.5% loss, but they are completely different patterns. They are completely different problems to solve. The 15% burst density, in that case, your burst state will arrive more frequently, but you only have 15% chance of losing a packet while that burst state is arriving. So your losses appear to be more spread out, more isolated. So this is where our forward error correction schemes that we have, the matrix sizes that we have in our codec, are most effective. When you get up to 80% burst density, your burst state is arriving less frequently. But when it arrives, you lose 80%. You have 80% chance of losing a packet. Similarly, if you have 40, 50, 60%. So you can see how this model actually measures the intensity of the losses, on a network. So with the 80% burst density, this is where your forward error correction scheme is going to fall apart. So this is where, we have to use other techniques, possibly in a combination with forward error correction, like interleaving and stream splicing, which is the most popular technique that we have, which sends duplicate packets with programmable time offset to absorb the initial bursts. So that's like the frontline defense. And then, typically what we've seen is that when we apply forward error correction on top of that, it is more effective in taking care of the residual losses. So what all this does is that it brings the packet loss rate down low enough where your packet loss concealment is very effective, right? Anytime we notice that the packet loss,
concealment.
Exactly. So you want to try to, if you're going to get a packet loss, you want to try to isolate those losses. That's when your concealment is going to work the best, right? So that's the whole idea. So you have a cascading, protection scheme with the stream splicing, forward error correction, and then obviously you have your concealer at the end. Does that help?
It does, and I want to go back and make sure I understand a couple of concepts of just a bit more. Let's talk for a minute about this forward error correction in the IP world, because I grew up as an engineer with forward error correction as being part of satellite communications, with just little frames of data, pretty short, and interleaving was done. And it seems as though this didn't add a whole lot of overhead. It didn't add a whole lot of complexity, and I actually think I understood it. But in the IP world, if you lose a packet, you've lost a lot. And I'd like you to help me understand what method of forward error correction can be effective in a stream of IP packets if you lose one or two packets. How can it seems like you almost have to send like double the amount of data that your forward error correction would take up a lot of overhead. So correct my thinking there.
So no, that's a good point. So typically we employ two-dimensional forward error correction. So I'll give you an example. If you have a 4x4 matrix, 4 columns and 4 rows of packets. So what happens at the encoder is that you fill the matrix up with the data packets that you're going to be sending, and then you compute parity packets for each row and each column, right? So this is what a two-dimensional forward error correction does. So unless you lose all 4 packets in a row, you should be able to recover that data packet at the receiver using the using the parity packets and the rest of the data packets. It does take a lot of
computation
at the receiver to recover other packets to recover your target packets, right?
Right.
That's why you have to limit the size of the matrix that you support in your codec. Otherwise, your CPU can be just bogged down just trying to recover
this is what I was going to ask you. How is 2x2 a typical proper matrix size, or what happens if you want to go bigger than that to correct a larger packet loss?
So 2x2 with two-dimensional is 100% overhead. So this is like doubling your capacity, right? 4x4 with a two-dimensional matrix is 50%, right? Because you're sending 8 parity packets in addition to 16 original data packets, right? So that's 50% overhead. And we also have lower overhead schemes also, 25%, 33%, but essentially the size of the matrix is what dictates how strong your correction is and the patterns of those losses, right? If you have a pattern of losses where you're losing 5, 6 packets in a row, that forward error correction alone is not going to really help you, right? And packet time also makes a big difference, by the way, right? So if you have if you have a stream that is 4 millisecond packet time, 4 packets is basically 16 milliseconds. So if you have a burst of 20 milliseconds, 30 milliseconds on a transmission link, on a wireless link, your FEC is just out, just gone out of the picture. That's why people say that FEC doesn't really work. But you really have to look at the bigger picture, right? What packet time you're sending, what type of network you're using, and we would never recommend FEC alone on a public type network or a high-speed wireless network where you're getting burst of errors, we would always recommend, to use stream splicing with time diversity, to get the burst of the errors first. And if you have any residual error, this is where forward error correction can help out. Bandwidth is getting cheaper by the day, and compression algorithms are getting better. So you have all these different tricks you can play with.
So from the forward error, and thank you for that explanation. I read a paper about this actually about 3 or 4 years ago, and your explanation there just helped crystallize what I think I read in that paper. So that's very helpful. A matrix is built, and the rows and columns of data are compared, and parity bits are come up with, and you can come up with enough parity information to make up for up to how many. Let's say you had four packets in this. How many could you lose and still make them back up?
Well, again, it depends on the pattern of the losses. So we have simulation, or I should say emulation data, where if you have 100% random loss rate, you can have 3 or 4% packet loss, and our forward error correction would cover majority of the packets. I mean, to a point where you would not hear, because the packet loss concealer is recovering or masking those isolated loss after that. So it all depends on the pattern of the losses, right? I mean, yeah, if you have the number of columns gives you the burst protection. That's the bottom line. So the matrix does not have to be symmetric. You can have 10 by 2, 6 by 4, 10 by 10.
Okay.
So it all depends on exactly what the patterns are on your network and how much CPU you have, to recover the other packets, to recover your target packets. Because you could lose 3 packets in a row, or up to 4 packets in a row, but your target packet, to recover your target packet, you need to recover other 3 packets before you can recover your target packet. So your decode type can be variable too. So there are a lot of factors with forward error correction to consider when you increase the matrix size, and that's why we use it in a limited manner on good networks. That's all you need. If you have a good solid MPLS type connection, you get isolated losses, throw in an FEC, that would do it. But majority of the public network connection we have seen it used in combination with our stream splicing technology, whether you use it with stream splicing with network diversity or with time diversity, or you can combine.
And that's the next subject to get into, because I had actually given a number of talks myself, not nearly as scientifically up there as yours, but I'd given some simpler talks on network diversity and time diversity, and a little bit about FEC. But thank you for again expanding my understanding of FEC. Chris, before we move on to a couple other techniques, do you have any comments or questions at this point? You've been Mr. Silent there in your transmitter room.
Well, I didn't want to interrupt or anything. I would totally agree with what he said about using, looking at your network, looking at what you have, and deciding which methods of error correction, I'll call it, you want to use, whether it's splicing, timing, diversity, FEC, the whole bit. I mean, I've been doing that for a couple of years with a lot of IP-STL links, and I have to say it's been very successful. But it is I'll call it a mixed bag approach. You shouldn't try and think there's one silver bullet to it. And since you can't control the network or the points in between A and B, definitely use the toolbox of solutions. I totally agree.
Gotcha. Okay. So the FEC is what we've been mostly talking about. Great for the random packet loss. But when you get a bunch of loss all at once, and Keyur, you've mentioned a few times stream splicing. And so there's a couple ways to approach this. And you mentioned time diversity and network diversity. Help us really understand both of these concepts.
Okay. So, or combination. You can actually use combination of the two. So network diversity is. So network diversity is what the trend is right now among the codec vendors, right? They have dual networks, streaming, so you can send 2 streams or duplicate packets across independent network paths. In fact, with our codec, we can actually send up to 3. Connect to up to 3 different network connections. You can send up to 3 different streams, duplicate streams across the network. That's what we call network diversity. But the network diversity has to be truly independent. That's what people need to understand, that these paths have to be truly independent, different ISP connections, and you have to do trace route to make sure that they don't converge at some tier 1 ISP and then go on the same pipe, because then you really lost your I would say randomness, right? Because essentially what you're trying to do is create randomness of for your losses by going the independent way. Now time diversity is when when people don't have that option for network diversity or or can't afford it, this is where we see that with the burst losses, forward error correction cannot work well. So we can send duplicate packets, multiple duplicate packets, not just two. Depends on what the network calls for, with programmable time offset. Now how do you get the time offset? So this is where Intraplex Live Look, is been really helpful to us. So this is the PC Analytics software, as I mentioned to you earlier. So it actually talks to our codec and the audio stream to collect statistical information and provides various functions. Right, one of the function is graphical trending of various statistics of the codec, and one of them is the Markov state models or the burst parameters. The other statistics you can trace is delay, jitter, how well your forward error correction is working. So by using time graph, you can tell, oh, my FEC worked well from 8 to 10, but 10 to 12, it didn't really work well. So beyond the graphical tracing and logging, which people use it for tracking the SLA, we have a reporting function that will summarize the data set that you want to analyze, right? We'll tell you how the losses are occurring, what the average packet loss rate is, were they occurring in bursts, were they occurring isolated, and at the end, it will actually recommend which technique would best work on this network connection, whether forward error correction would work or whether stream splicing with time diversity, and will actually tell you the time delay to program in between the duplicate packets by doing the burst analysis of the burst in the data set and comparing it against the simulation points that we have in the application itself. So we have thousands of simulation points in the application that were created with different impairment models, and then we have recovery that work against the impairment model. So when the tool analyzes the current data set, it will use a decision tree algorithm to find the best fit, and that's what gives us the time delay value. Now, again, this is not an exact science, so it's a good starting point. It's the visibility that you didn't have earlier. So yeah, so that's the whole explanation about time diversity.
So as a practical example with time diversity, let's say that I had only one IP connection on a link. Maybe it's a studio transmitter link. Maybe it's carrying some audio across the country. And I'm finding that I'm getting burst losses, so a number of packets in a row. And I'm finding that the length of this burst is almost always under 300 milliseconds.
Right.
So this is, but I'm losing almost every packet in that 300 milliseconds, and that's the characteristic that I have. So my time diversity would be what would need to be greater than 300 milliseconds.
Right. Yeah. Right. And the buffer would be adjusted automatically. So receive buffer will adjust it automatically. So we have a technique which we call adaptive receive buffer. So if you adjust the time diversity on one side, the receive buffer will see that, oh, the other stream is coming in late, so it's going to increase the buffer. But you can do that manually as well. And we have tremendous buffering capability to allow for seconds worth of diversity. I'll give you an example. One of our customers was using HughesNet for the backup audio, and he was
satellite,
satelliting, right? So he was getting 500 or 600 milliseconds of burst of errors. He ended up actually using, sending two streams. They were almost like a second apart just to be sure. And because this was a return confidence monitoring, he didn't really care for the delay as long as this, audio was coming in clean. He increased the buffer, sent a couple of streams, second apart, because he was able to see that with Live Look that, the burst size is always around 400 to 500 milliseconds. So he was able to actually send multiple streams, to overcome that burst loss. So this is where Live Look kind of, brings everything together, right? If you just, it's not hard to send duplicate packets with time diversity, right? There is no innovation there. It's what brings this together is the analytics tool that kind of guide you as to what you need to set that parameter to. That's why Live Look is the important component of our reliability story.
Thinking about, let's say that as in my example, and maybe I'll change my example a bit, but let's say I knew that 90% of my burst losses were under 300 milliseconds, but 10% of them were over 300 milliseconds, and that 10% was all under 600 milliseconds. So is it possible to do the time diversity, but have it be dynamic? Is that
Yeah.
is
Yeah, it can be done. We are actually working on a dynamic algorithm as a result of what the analytics tool tells us. But at this point, you would have to kind of detect that. You can send more than one stream, by the way. With time diversity, you can send one stream, half a second apart, another stream that's 700 millisecond apart. We have customers that have sent 3 or 4 streams because they were using AAC HE at 48 kilobits per second. It was nothing. The audio sounds great with AAC HE V2 with 48 kilobits per second, and they had plenty of bandwidth to work with. So yeah, you can send multiple streams, but you'd have to do this analysis on your own. There is no dynamic algorithm at this point in the system, whether in analytics or in our codec, to kind of adjust time diversity as it changes. But you will get alerts if your recovery is not working the way it should be working, which should prompt users to say, okay, let me see what is going on. I'm going to run the report again and see what else I can do. But we give you the tools at this moment, and people have to take time to kind of understand the tools.
So at the receive end, let's say I'm receiving 2 streams, each of them with time diversity, and as you mentioned, one with a less time diversity, one with more. Would I want to set the buffer at the receive end to accommodate the longest time diversity of the 2 streams, or would I put up with a temporal switch if it had to switch over between the 2 streams?
Yeah, so we go for the hitless. So we go for the hitless method of stream splicing. So therefore, our buffer accommodates the longest delay, whether you're sending over multiple network paths or whether you're delaying over one network. So that's another important point that you brought up. For stream splicing with network diversity to be truly hitless, the receiver has to know the relative network delay, right, of duplicate packets as they're coming in. Let's say you have one path that is point-to-point wireless over your 5.8 gigahertz. You have no delay on it, less than 5 milliseconds. The other path is over cable modem, 400 milliseconds. So you have to kind of know at the receiver that, this stream is, has a delay of, this network has a delay of 400 milliseconds. So my buffer needs to be, at least 500 milliseconds deep for me to provide a true hitless type protection. And this is one of these capabilities that we added last year, is to measure the relative network delay between the various network paths that the receiver is getting, so we can adjust the buffer automatically.
Keyur, by the way, for those of you just tuning in, we're talking here on This Week in Radio Tech with Keyur Parikh. He is a development engineer and a product lead at GatesAir. And we're talking about really in-depth methods of trying to make sure that your IP packets or your audio is continuous, even if IP packets are lost, stolen, or mixed up on their way from the sender to the receiver. Chris Tobin is with us as well, and we're going to take a commercial break here in just a minute. But I do have one more question for Keyur before we go. Actually, I probably have 2. But you talked briefly, Keyur, about concealment. And I've talked about this a lot with the AAC family of codecs from Fraunhofer, that they can put up with a certain amount of packet loss, and the listener either doesn't realize it or it doesn't sound too bad. So this is useful in transmission as well. You don't have to correct every single packet if you're using a concealing codec. Yeah.
Yeah, that's absolutely correct. The concealment algorithms that are part of the AAC family of codecs from Fraunhofer is what you're referring to, are good. I mean, the energy substitution. We also apply another concealment method. We replay the last packet as well, but we stop if it goes beyond 30 or 40 milliseconds because we don't want it to sound repetitive or discontinuous.
Right.
So. Yeah, so it all depends on which algorithm you're using. With uncompressed, obviously you can get away with just replaying 3 or 4 packets. People won't even know it. With the AAC, LC, HE, the Fraunhofer algorithms, have good concealment algorithms. My feeling is that they work well as long as you are concealing, maybe 1 or 2 frames at the most.
Right.
But then beyond that, you can actually hear it. Anytime you go above 40 or 50 milliseconds, you can hear it.
So I remember my last question before we break. Tell me about, all this streaming we're talking about is done with UDP. We send the packet, We expect it to get there, and we take other mitigating, other methods to mitigate it if they don't arrive there.
Right.
Exactly what we've been talking about. Is there any role for TCP in media streaming?
So that's a very good question. I would say yes for certain networks, but TCP, the base TCP stack has a problem with packet losses, as you know. Anytime there's a packet loss, it assumes it is due to congestion, and it restarts its window, and congestion avoidance logic also kicks in. So that slows your streams down. So, unless you have modified the TCP stack to keep the window full, which is what the satellite guys have done, at least we have done that at Hughes Network System, the TCP has problems with just generic packet losses that are not due to congestion. And you get a lot of packet losses because not due to congestion, due to transmission errors, as you know. Now, the other issue with TCP is that and reliable UDP, by the way. There are also protocols that does reliable UDP. So
I'd like to know about that. Yes, at some point.
Well, we don't employ that, but it's very easy to create a reliable UDP protocol. But the problem with any type of retransmission scheme is that the amount of time it takes to get the packet retransmitted, may not be suitable for a lot of the media application. The other issue is with we send our audio in a lot of the cases on unidirectional link, like the 950 megahertz link in the US and in Europe. We multicast quite a bit, and obviously TCP cannot be used there. But the bottom line is, if you look at any interoperability standard, whether it's for voice over IP, for video over IP with SIMT, and audio over IP, they all recommend using RTP UDP. So if nothing else, for broadcast streaming, I think for interoperability you have to support RTP over UDP. But I would not rule out TCP. If the network conditions are adhering to the inherent flaws of TCP.
Well, you're watching This Week in Radio Tech. Chris Tobin's with us. Chris, I don't know, man. My head is getting pretty full here with all this information. How about you?
Oh, this is great information, and actually a lot of it I've toyed with, and I've played with the network emulators to create trouble on my network to see how the codecs I've been playing with function. And so far, everything is mentioned is spot on. And we've been saying this for 2 or 3 years now, when we talk about IP linking. And that you have to take a more aggressive or more proactive approach to how you connect, and the more analytical information you can get from the network, the better. So this is spot on. The one thing when we come back from break, though, I'd like you to talk about is, if your broadcaster, say, doesn't have the luxury of 2 ISPs, diversity of any type, but has to rely on a single connection, cable modem at the studio, and we'll say cable modem at the transmitter site because they're particular part of the country. That's the services they have. What would be the best combination? Think about this combination of error correction, concealment you can employ to get the best of what may be expected on the network connection. Just
good deal.
Curious.
So when we come back, Keyur, think about the best answer to. I've only got one connection at each end. That's all I can get. So dual is not an option. Well, what's the best combination? And I bet the Live Look software can help you determine that. Hey, it's episode 301. We had episode 300 live from NAB. That was cool. And actually, I didn't get to meet him there, but Keyur was just down the hall. He was just a few booths down, and so busy there, we didn't get to get out and shake hands. Our show is brought to you in part by the folks at Omnia. And, oh, my goodness, we had so much activity at the NAB around our Omnia kiosk. Certainly, Cornelius Gould, a fine architect of audio processing, was there. He was swamped, and he was showing people all of the audio processors that were there, focusing on this new Omnia 11 with 3.0 software and his new G-Force thing. It's amazing. I got to get him on to talk about that. So I'm not going to talk about the G-Force and the 3.0 right now because I don't have enough information, and it's not shipping yet. But it will be. There's a sign-up page actually on the website on the TELUS Alliance website. You'll find a link somewhere there to sign up for information about Omnia 11 3.0 and the G-Force software for the Omnia 11. Just amazing stuff. But what I do want to tell you about is the variety of audio processors available from Omnia. Whether your budget is very limited and low, whether you've got a mid-price budget, or whether you've got, hey, sky's the limit, I want to put the best thing in here, I've got to be competitively loud and sound great in this market. Well, Omnia's got something for you. Anywhere from the Omnia 1, you have then from there the Omnia 7. There's a 7 AM now and a 7 FM. There's the Omnia 9 and there's the Omnia 11. So quite a range of processors. And, they're really a lot different in their philosophy. So, hey, it doesn't mean that an 11's better than a 9 or a 9's better than 11. You may try them both and choose the one that really just works out best for you. The Omnia 9, for example, it has everything but the kitchen sink is in this processor. You can do FM processing, your HD1, your HD2. I think you can also do an HD3. You can certainly also do processing for audio streams, and it even has audio stream encoders in it. So you can do your streaming, whether it's confidence monitoring streaming or whether it's your actual stream that's going out to a CDN to the rest of the world. You can do that inside the Omnia 9. Lots of other functions available too, especially the undo and declipping. People just love that. And the stereo embedding that gives you a demodulated up to 140% audio left and right while keeping your modulation at 100%. It's amazing. I still don't understand how that works. The Omnia 11, on the other hand, my goodness, that processor has one job. Now, it'll do your FM and your HD at the same time, but that Omnia 11 just does that one job so well. You'll hear music through an Omnia 11, and it just, have I heard this mix before? Is this a new mix? I'm hearing detail in this song I've never heard before. I'm hearing voices just cut through so clearly that I can just hear everything. The Omnia 11, people around the world are loving this box. And the Omnia 9 too. It just depends on what you want. So if you're not sure what you want, you can try them both out. Or maybe you've got a sister station or another station in your group that's using an Omnia 11 or an Omnia 9. But check them both out. Check them all out. Hey, at my radio stations, we're using an Omnia 1 at one of our stations because that's what we can afford. And we also have a few Omnia 3s. Even these Omnia 3s that are 10 or 11 years old, still going strong and making some of my stations sound just terrific. There's also the Omnia 9 SG. That's a standalone stereo generator. The idea is you feed it pre-processed audio, although the Omnia 9 SG does have final limiters and clippers in it. It's got part of the Leif Clayson Omnia 9 toolbox inside the SG, and then it gives you a beautifully perfect stereo generator output. Great for stations where you have distribution networks to multiple stations. That works quite well. Or if you just want to put a less costly item at the transmitter site, you can instead put an Omnia 9 SG out there and have your expensive processor back in the studio. Lots of possibilities. Check it out at telosalliance.com and then click on the Omnia or the audio processors, and you'll get to see the whole range there of Omnia audio processors. Love them. Got them on the air myself here at my stations. In fact, at all my stations, every one of them, we have got Omnia processing on the air, and that's about 9 radio stations now. And I know that, of course, there's thousands of them out there. The Omnia 1, there's over 12,000 Omnia 1 processors out in the world today. So we thank you very much for your support, your suggestions, and checking out new products like the Omnia 11 version 3.0 and the GeForce. Thanks, Omnia, for sponsoring This Week in Radio Tech. All right, it's episode 301. Chris Tobin here, and so is our guest, Keyur Parikh. And Keyur, let's see if we can answer that question. You've only got one ISP. You can't do dual connections. What's the best thing I can do? Or how do I determine the best thing I can do?
Well, so the best thing to try at the codec level is to use a compressed codec. I love Opus, but I think to try out how the network is behaving, I would go with the AAC HE because you can reduce the packet rate with the AAC codecs. AAC HE is with 48 kilohertz sample rate is around 42 milliseconds per packet, and we also allow you to pack multiple frames in an RTP. Depending on your coding rate, you don't want to fragment the packet. I always tell the customers, you want to make sure you don't send fragmented packets out into the network because those can be treated differently by network elements in the middle. So you can play with the packet rate with AAC codecs. I like AAC HE in this case. And then once you figure out the codec and the bit rate that you want and use the live look to to see how your network is performing. If you're getting, more than likely you'll be getting burst of errors. With the simple ISP connection. Now, in that case, you would have to send more than one stream. So since you have already reduced the data rate, you have more bandwidth to play with. So if there are any route flaps or things like that in the middle, you can adjust the number of streams that you're sending and add forward error correction on top of that. So that's the beauty of the technology that we have, that allows you to scale the protection, based on what the need is for the network. It doesn't limit you saying, oh, you can only send 2 streams, or you cannot use forward error correction with that. So we allow you to scale up the protection depending on what the live look tells you, or is happening. Even after you added this, it'll tell you, well, you're still getting packet losses, and this is the kind of packet losses you are getting even after you added stream splicing. So yeah,
I'm sorry. Go ahead. I was going to ask you which GatesAir codecs does the technology you're talking about? Which do they appear in? Which products?
Well, I'm talking about the IP-Link codec, IP-Link IP-Link platform, all of them.
Okay.
Yeah.
So last I looked, there were 2 products in that line. Are there more than 2 now? Or is it?
Yes.
Oh, plus the Interplex cards too. You have cards for Interplex.
So that's a different platform. So the original multiplexer family that we had, the T1 E1 multiplexer with the modular channel cards, they are still there. A lot of radio stations still have that. We have an IP version of the T1 E1 card, so you can just swap out the T1 card or an E1 card in Europe for that matter, and boom, you're in the IP domain. Now the IP link, the audio codec, platform is completely different. There's a single channel product. There's full duplex. Then there is 2 channels, 2 stereo in, 2 stereo out, with the GPS capability for single frequency FM technology that we have, patented technology that we have. And we have introduced recently an IP-Link 100P, which is a single channel that also has a GPS capability, but has the front panel display with the fancy VU meter. So essentially, there are 2 variant of the products, so 1 channel and 2 channel with options for GPS timing.
Gotcha. Okay. All right.
For audio,
Chris?
but then we have products that do composite FM as well, both AES 192 and analog composite FM.
And that's a whole other subject. We're going to cover that on some other show. There's MPX over IP. Pretty interesting stuff. So the other thing that's been in the news has been network security for IP. And I think that the cases that we've seen where people have had a problem, they were probably not being very smart about their security. I know of, sorry to say, I know there are stations right now that have an EAS system that is, I guess, in their DMZ of their router. It's just right out there on the internet. You can Google some certain words and find them, and if they haven't changed the password and the default passwords, you can get right into a station's EAS gear right now, and it's just a shame. Now, that's an extreme example of people that have IP codecs. If you know about open ports and you know about an RTP receive port that's just sitting there waiting for packets to appear, or maybe you can flood with other packets, these could be very vulnerable. Maybe there are other cases, Parikh, so I'd like to start to hear your take on what the problem is now and how people should be avoiding the problem.
Well, so, we did a paper last year also on network security, more focus on the audio over IP codecs that are just one segment of the broadcast chain. I mean, really, you have to protect the entire broadcast chain, because every element from your AES 67 gear in the studio to importer, exporter, automation system, and all the way to the GUI of the transmitter, entire chain has to be protected, because they're all going towards IP. So from an audio codec perspective, so the paper covered vulnerabilities both at web interface level, which is what is exposed to the public internet. For example, brute force attacks. So even if you have changed the password, and you have SSL, you are not immune from brute force attack or a dictionary type attack. Somebody trying to guess the user's password. We also talk about reconnaissance and leading to intrusion and denial of service type attack. So we talk about being able to provide network access control capability right in the codec as a last line of defense, which is what we support. And we also talk about media plane, threats because of the use of unsecure versions of SIP and RTP. As you just rightly pointed out, RTP by itself, natively does not have any authentication, nor does it have any encryption. So you are vulnerable to eavesdropping, as well as the worst case is media hijacking. Somebody could be sending the RTP packet to the decoder in exactly the same format it is expecting, by sniffing the SIP packet, the SDP packet. And unless you have some other level of filtering going on, you'll start playing out. The decoder will start playing out the attacker's audio and would consider the real encoder's audio coming after the attacker's audio as duplicate packets and discard them. So there are a lot of threats.
Yeah.
So there are a lot of threats that we talk about in the paper, and then we could talk about the countermeasures. Specifically, we talk about the network access control capability that we have. So every packet that comes in, we have multiple layer of filtering that happens. At layer 3, we have something called the IP access control. So if you enable this filter, if your source address is not there, then that packet is discarded right at the driver level, so right at the ingress. It doesn't even get up to the IP stack. So we've done a lot of modification of the IP stack of the operating system that we are using to reduce the CPU utilization, due to the action of discard. Right. Same thing with layer 4. We give the users the ability to turn off web service, SNMP, SIP. SIP is notorious nowadays. We also allow people to turn off fragments, IP fragments. If you don't expect fragment on a particular interface because you're not sending fragments, only sending perfectly, MTU packets well within the MTU size, there is no reason for you to get fragments. So we allow you to turn fragments off. They can be a source of attack vehicle as well. So layer 4, there are several controls that we provide to the users. They can turn them off on a per interface basis. And then SIP, I can't tell people enough. You leave your SIP server on on a public internet, you'll start getting incoming call requests from G7 for G711 and G722 calls from unknown devices out there. Same thing with SNMP. We have seen unknown managers trying to access our standard MIB table, which most networking device vendors support, the MIB2 RFC 1213. If you leave your public read-write password open, just like you said, not changing the password, you will get bombarded with requests, and it will affect the performance of the audio codec. So it's important. It's important to have those type of network filtering capability. I wouldn't say firewall, but network filtering capability within the codec. It's not going to protect you against distributed denial of service, because codecs are not designed for handling high rate of packets, and still be operated. But it is going to give you the last line of defense, enough deterrent for hopefully somebody would just walk away and go to the next device on the list.
Yeah, and that's important. I guess most hackers, I call a lot of them script kiddies, because they are often just young, mischievous people running a script to try to do things. Good, a lot of good tools there that you mentioned. I didn't realize that some of those were in there. What about users who say, well, we establish a VPN between our sites and then we run our IP audio through that? What are the benefits and what are the possible pitfalls of using VPN tunneling?
Well, so obviously the benefits is that, if it's a layer 3 VPN, which is what I would recommend, IPsec type VPN, I would not recommend SSL type VPN, because SSL runs over TCP and that can impact your audio because it's retransmission. IPsec works at layer 3 is what I would recommend. Obviously you protect yourself from both eavesdropping as well as authentication, right? You know exactly where the packets are coming from. So VPN, there is really no downside. The only downside I can see is that if you are sending high rate of packets through, then you want to get a high-end VPN device to make sure that it can handle not just the data rate, but also the packet rate you are sending. We had a customer, sending on an old VPN an uncompressed stream, and was wondering why, when the VPN is in between, he's getting packet losses versus when the VPN is not in between. I said, change to compressed codec and tell me what the results are. So you want to make sure that you get the right VPN as far as the load that the encoder is generating.
And this is with an uncompressed stream, and this is typically going to be what, 2.5 megabits per second for a typical linear stream, yeah?
Yeah, it depends. Depends on the packet time, but you're right. Yeah.
So you typically have a maximum MTU, right? So don't you? So it ends up being a lot of packets per second to get.
Yeah. So the packets per second really with the uncompressed stream is dictated by the packet time, right? So if you have a 4 millisecond packet time, you are generating 250 packets a second, right?
Right,
if you're sending 1 millisecond packet time, which is the default for AES 67, that would be 1,000 packets a second time. And if you say, well, I got a 10 meg pipe with VPN boxes, and I'm going to extend my AES 67 from studio to the transmitter side, you better make sure that VPN can handle 1,000 packets a second. That's the point.
Gotcha.
We have
that's good. Good.
Yeah, so we allow users to build the packet. So with 44 kilohertz sampling, we allow them to go all the way up to 8 milliseconds. We don't allow people to go beyond 1500 byte. We don't want people to send fragmented packets out because different devices handle fragments differently and can cause unforeseen issues.
And when you say fragmented packets, are you really referring to some odd number or some fractional number of frames within a packet? Or help me understand what you mean when you say fragmented packets.
IP fragment. So when the Ethernet packet exceeds the MTU of the device will fragment it. So you want to make sure what your maximum MTU size is for the patch. Generally, it's going to be 1500 bytes nowadays, unless you have some wireless link. So, we won't allow you to build up more than that. That's what I'm saying.
So what happens if your codec is making packets that are right up close to the MTU, and then on top of that you tunnel through a VPN? Can you run into problems? Do things get fragmented that way? Possibly?
Possibly, absolutely, possibly. That's why you want to run your path MTU to understand what the maximum packets size you can send. So that's why we are then you can say instead of 8 milliseconds, I'm going to send a 5 millisecond packet, and then that would give room for the VPN headers.
I do want to mention to our viewers and listeners, we've talked about two different white papers that have been presented by Keyur and your colleague. Is it Junius Kim? Is that his name?
Junius Kim, yeah, he's my partner in crime.
Okay, so I will have links to these two papers, and they're both excellent, and they go along perfectly with what Keyur's been talking about here. I'll put links to these in the show notes. So if you go to our website, thisweekinradiotech.com, this show will be posted in a couple of days. Of course, you can see all our previous shows, and also on gfqnetwork.com. Same thing, you'll see the show notes there. Chris Tobin, we're running close to being out of time, and my goodness, this has been fascinating. And part of this is over my head, and part of it's just right at my level. Oh, I'm getting this. I might forget part of it later on. Tell me your thoughts at this point, and what you want to ask Keyur, if any follow-up questions here.
Well, actually, I do. With the analytics, would you be confident to say go to an ISP and say, look, here's what I've been observing on my network connection I'm paying for, and here are the stats I can show you? I'm saying this because in the days of, say, ISDN and stuff, you had the CT100 tester that people would bring out, and it would, if you had one of those on site and the phone company came out and you're having issues with your ISDN, you'd say, look, I tested a line, here's what I'm getting for bit error rate, there's a problem, can you please check it at the CO? They would look at you and say, okay, you're using the same box I use, therefore I'll trust what you're saying, and I'll test it again with mine. How does someone in the IP world use the analytics, say, of your product or any other product or a device to go to an ISP and say, look, guys, I got this circuit, it's been working great for 6 years, and all of a sudden I'm seeing error rates, I'm seeing packet loss, all kinds of craziness. Can you use this stuff in a way that the analytics so that they understand it and go, okay, you're right, there must be something, let's work together and come to a solution? Or do you still have to find what they're using as their method of measuring their network reliability and to solve your problems?
No, that's an excellent question, Chris. So typically, when somebody calls up, complaining about the network losses, if you just provide number of packets lost, the ISP will run a ping test, 24-hour ping test. Will probably send one packet a second. Your audio stream is sending, if it's compressed, it's probably sending around 50 packets a second. So it's a different load than the ping test that they're running. So what the analytics tool that we have provides is the analysis of the packet stream as it enters our box. Now, if you have other devices on your premise, before our box, such as the router that's faulty, then it will not be able to distinguish whether the fault is coming from the router or coming from the network. Do you see what I'm saying? But it will give you what the audio codec is seeing as an input to the stream before it actually does the correction. So it give you the before and after view of your stream. In between is the processing block, which does the packet loss recovery.
Right. So okay. Well, yeah, that's perfect. So what you're saying is it's like the days of T1E1 where you did a BERT test to find out what was wrong with the T1. You'd run the BERT test overnight, and you get your errors on your smart switch, and then you go from there. Perfect.
Right.
So what you're probably saying is the best approach or best practice would be if you suspect there's a problem with your ISP, bypass your router, put the box, the codec at the ISP port, and run your test as if you're doing a T1 BERT test, with a T-BERT or something. Okay, great. That's because these are the things I get questions for lately, and I'm like, I've been using the box as device, and most ISPs I've talked to have been pretty cool because I've been able to demonstrate that I understand where they're coming from and we can work together. But I know there's a few out there just look at you and go, we use this is our method, sorry, goodbye, thank you very much.
Right.
So, and you're right, the ping test has a perfect, I'm glad you mentioned the difference in the packet size and what was going on per ping. Yeah. So that makes a big difference, the load test.
Guys, we've got to take one more quick break. We'll be back, and I want to see if I can get a tip, maybe some tip of something to read, a tool to use, a piece of software that's excellent. Of course, we've heard about Live Look. I'm sure that's excellent software. It works with some of their products at GatesAir. So when we come back, Keyur, if you have a tip that you could leave our listeners with, that would be just super. Sorry to surprise you like that, but I'm sure you can think of something. Our show brought to you in part by the folks at Axia and the Axia Fusion AOIP audio console. This thing is beautiful, and it's amazing. We had one of these at the NAB show, and in fact, I got to tell you, we're not offering it for sale yet, but we have a developer in France who has built a touchscreen module. It matches the metalwork just fine. It goes right into the Fusion console, and it gives you a lot more functions on this beautiful little touchscreen display. Lots of metering, lots of controls of I couldn't even get to it. Lots of macros that you can do. Just amazing stuff. And my point in bringing that up is not to say, hey, wait for this product to come out. My point is that you too can develop accessories to go along with your console. There's ways that you can work with the folks at Axia to develop ways to make your console more fit maybe the way you want to work. So, hey, look, there's thousands of these out there, and most of those thousands are just like they came from the factory. But there are users in Australia, in England, in France, and a couple other places where they've developed something to go, either a hardware or some software to enhance the functionality of their Axia console. Now, you want to check out the Fusion console. It is absolutely gorgeous. It's got these bright OLED displays that show you exactly what's on the air, what's coming in each fader. It shows you confidence meters for what's coming in audio-wise. Also, what's going out. If that fader has a backfeed to a headphone somewhere, or to a codec, or a hybrid, or even a backfeed over phone line to something coming in over satellite. In other words, it doesn't have to be the same path. This will show you the backfeed level. It'll show you the status of, are you talking to the backfeed or not? This console, first of all, it's easy to operate, but second of all, it does so much under the hood. When you press the talkback button to talk back to someone at the other end of something, it's amazing all the stuff that goes on just under the hood that it takes care of automatically. And I couldn't even start to go into all the stuff it takes care of automatically. It just does. It just works. Being an AOIP console, and maybe if you haven't gotten to install an AOIP console yet, you'd learn something installing this one. Any fader can be any input. In other words, you no longer have the concept of, well, microphones have to go on these because these are mic faders or mic inputs, and line level things go on these, and I have some AES faders over here. That's all out the window. With audio over IP, any fader can do any function. You can swap them around even from show to show. I mean, if you've got somebody who for some reason prefers his mic fader on his right hand, you can do that if you want to. Just load a different profile. So much you can do with this console, and it's so beautiful. It's so easy to use. I just got to encourage you to check it out. There are videos on the Telos Alliance website, that series of videos that go through the Fusion console, its design, workflow, characteristics, how impervious it is to getting hurt. It's really strong. And these are just great short videos. They're about 4 or 5 minutes long a piece. Here's what you do. Go to the Telos Alliance website, telosalliance.com, and then go to the Axia panel and look at the consoles. Click on the Fusion console. You can get it in all different configurations. Split console, place the faders wherever you want, put a telephone module in there or not, whatever you want to do. Intercom, you can put intercom in there. And there's some videos off to the side that you can link to and take a look at those, where Clark Novak goes in very much detail explaining these. By the way, speaking of videos, I got to tell you, the Telos Alliance YouTube channel is amazing. Oh my goodness, go to YouTube and search for Telos Alliance. We got a channel there, and different product lines. We have white papers being delivered, Dr. Barry Blesser, Greg Shea, Corny Gould. We have, of course, a lot of presentations on there by me, product demos, product explanations, and just amazing. It's really worth your while. Make that your second stop after you go to telosalliance.com. Check out the Telos Alliance channel on YouTube. Thanks, Telos Alliance, for sponsoring This Week in Radio Tech. We sure appreciate it. All right, Kirk Harnack and Chris Tobin, episode 301. Our guest is Keyur Parikh. And Mr. Parikh, would you happen to have a tip for us this week?
Well, just going with the topics, I would say, network security is going to become a concern, as we move on the IP path. I mean, voice over IP, which is the application that I came from, we had gone through the same thing. As more and more gateways started to get deployed, we started to see more and more intrusion, penetration. So I mean, and this is a bigger impact problem. This is one-to-many communication. So I would say, people that are in charge of the broadcast chain, to be aware of all the different elements that are there, and be aware of the security on them. If they're Windows PC, you got to make sure that they have malware on it, or you restrict human error on those Windows PCs. If you have codecs that have access control list, use them. So network security is the tip that I would say that they would need to get more familiar with, all the different ways that their broadcast chain can be broken. And have option plan against those threats.
And for engineers who are already at least familiar with networking and networking concepts, I think a great place to start is Keyur's white paper on this, which again I'll put that in the show notes. Thanks a lot, Chris Tobin. Anything for us before we have to leave?
Yeah, just the simple stuff this time around. Lights. Well, yeah, in case you have you work at a transmitter site, this is a Nortel flashlight, by the way, LED light. And those of you that have them know this is only available at the Nortel Users Group every NAB. That's it. Can't get it on Amazon, sorry. But the other thing I wanted to point out, I missed it. you didn't stay long enough. You were taking pictures and videos of other people. Yes. And the other item that I found very handy in the last couple of years, and I keep meaning to talk about it, are these little flashlights you can get. Now, this may seem like nothing at all, but the best part about it is when it's plugged into a utility outlet, the light goes off. And if I drop this down, then the switch works. The great thing about this is you put this in the non-generator circuits at the studio and transmitter, and in the event of utility loss, these lights will pop on. Even though you may still have lights above you, you say, oh, we're on generator because my little flashlight's lit. I know it seems crazy. It seems way too simple in this world of smartphones and IP security, but something to consider at sites that you might need extra lights when the generator or something doesn't go right. The studio.
That's it's a great idea. I actually used to have one of those flashlights, and at the house, I'm sure it's dead now, but I never thought about putting a transmitter site. It's a great idea. And if you don't have a generator, like so many of us don't, you go on the site and you've got a little bit of light in there from this flashlight that's burning because the power went off. Cool. Thanks, Chris. All right, and I've got. Oh yeah. Oh yes.
It's plenty of light. You can see me very clearly. So that's what I'm talking about.
They're looking like a CSI episode there with the flashlight flashing at the camera as they look around for the dead bodies.
There you go. The time of death, TOD. Oh boy.
Yeah.
I'm in broadcast. It's already happened.
So I don't. Thanks for that tip, Chris. Very good. I don't have a tip per se, but I've got a piece of equipment that we actually had on the air for about 45 minutes to an hour today. We moved some of our STL here at my stations in Cleveland, Mississippi. We moved from a standard analog 950 megahertz STL to the IP radio link that I established here almost a year ago. Now, we've had one station at the transmitter side on that IP link. Today, we moved the other station onto it full time. And now the analog STL is a backup. Well, we had to move the audio processor from the studio to the transmitter side. We have an Omnia 6 we had to move. And while we were moving it, we had to have a processor to stick on the air on the analog link. And I have this one right here. This one was made by Broadcast Technology Company in Lamar, Colorado. And I want you to see that this was one of the very first ones made. And it's so early in the production that it actually has a big spelling error on it. It says Ultimod FM. It's supposed to say Ultramod, but it doesn't. It says Ultamod. And that, I was told, was a mistake. It was silk screened without a good spell checker. And that's how old this is. But you know what? It worked. It wasn't the Omnia 6 in terms of loudness and clarity, but it was clean. It was clean, and it did exactly what it was supposed to do. So my tip, if you want to turn that into a tip, is, hey, engineers, and I'm sure you're doing this, but keep an extra processor around, for when your main one dies, or you need to move it to the transmitter site or just rewire or do something with it. Good to have an extra processor. We got to go. We're out of time. Our guest, Keyur Parikh, thank you so much for joining us. Yeah, your talk has been stimulating, interesting, and I'm going to have to watch the show again myself to try to understand it all.
Well, thank you for having me.
Thank you again, and I'll put your paper links certainly on the show notes so folks can read over those. All right. Thanks again, Chris Tobin from a transmitter site in New York City. Thanks for joining us as well. Appreciate you being there.
You're welcome. This was a great show, great guest. Everything was it was perfect. Look forward to the next week.
Next week, we're talking about some radio virtualization making lots of radio happen in smaller boxes and having it virtualized that way. This technology is coming, so I think we're at the early stages of it. Yeah.
That's common practice now in most office spaces. I've been doing it on a couple of servers, so it's pretty cool technology. It's a cool approach to doing things, and in the world of studios and consoles and all kinds of crazy stuff, virtualization sounds pretty cool.
It does. We're going to learn more about it at these early stages. Hey, our show brought to you by the folks at Lavo, also Omnia, and at Axia. Thanks very much to Suncast for producing today's show. Great job. Appreciate it. And thanks to Andrew Zarian and the GFQ Network, where you'll find plenty of other fine podcasts. I'm Kirk Harnack. Tell your friends about This Week in Radio Tech. I met a lot of fans at the NAB, and glad you're a fan too and watched it. But yeah, we did, didn't we? Tell your friends, and hey, set your DVR or your podcast catcher for downloading it. That would be great too. I'm Kirk Harnack and Chris Tobin. We'll see you next week on This Week in Radio Tech. Bye-bye, everybody.